All right, so the goal is to give you a rigorous version of the log-Kummer correspondence for tensor products of local fields or extensions of p-adic fields. To do this, I need to set up some categories. So this video is about the prerequisites in notation. So this is kind of well, it's something we have to do, right? For the log-Kummer correspondence and Ind3. So the log link indeterminacy. All right. So let's define. So let's go. All right. So let's do partially defined maps of sets. So we're going to define a category. So this is the category of sets with partially defined maps. Maps. And then the objects, of course, are going to be sets. And the morphisms. So these are going to be partially defined maps. So this is going to be a function. So a morphism is a function f from s prime to t, where s prime as well. And so let me give. So this is the category. Okay. So let me just make a couple of remarks about it. So so terminology. So remarks. So first, so given f from s to t defined on s prime, we call s prime the domain and we write it like this. Okay, so here we have this of G composed with F. So this is F inverse of the domain of G intersect the domain of F. Okay, then what else do we have? So that so given so a partially defined map then and a subset of S, then f of a will be defined to be equal to f of a intersect the domain of f. Okay, so that's what we mean by this. And is there anything else I need to do? Okay, so that's it. So let's do some examples. So the primary example is going to be, say, log. So this is a partially defined map, so the p-adic logarithm. And so the domain of log k, so this is OK cross. And we will have things like log k squared of k. So this is going to be log k of OK cross intersect log k of OK cross. Okay. All right. So this is we defined. That's our first category. So the second category we need is partially defined maps of monoid sets. So this is like a G set, but for an M set. So we're using the idea that an M set is a a set with a monoid action, and the maps are equivariant in the usual way. Okay, so the category will be denoted by M set here. Okay, so now we'll define the next category we need to define is M set. M sets P. So this is the category of sets, monoid sets with partially defined maps. So this could mean a couple things, and this is why we need to clarify it. It could mean the maps of monoids are partially defined, or the maps of sets are partially defined, or the actions partially defined. What do we mean? So the objects here. So these consist of M and S, where M is a monoid, and S is a set. And M acts on S, so with an action. And then a morphism here from M1 S1 to M2 S2. Okay, we could maybe let's write this with a dotted line actually. Oh, I could have made it dotted right there. Oh man, I did it again. Okay, I missed opportunity, right? Okay, so so this is so it's a pair F and G. Of course, one's going to be a map of monoids, one's going to be a map of sets. Well, F from M1 to M2 is a morphism of monoids, and then G from S1 to S2 is a partially defined map of sets. Such that G of M1 dotted with S1 is equal to F of M1 dotted with G of S1 whenever we have both things. M1 dotted with S1 is in the domain of G, and S1 is in the domain of G. Okay, so it needs to be equivariant when both of these expressions make sense. Okay, that's the point. All right, so let me just mention that a lot of the time when we do this, we say, so F, G, so this map of, partially defined map of monoid sets. Oh, okay, this time I got it. So is vacuously equivariant. If and only if for all M1 in M1 and all S1 into S1, so if this is in the domain of G, or let's say domain of G, and S1 is in the domain of G, right? So if we have this implies that M1 is equal to the identity, right? So, yeah. So I just wanted to add a quick picture of what a vacuously equivariant map could look like. So so here, or vacuously or equivariant monoid action here. So so what can happen is that you have a partially defined map of sets. Say it's defined on this domain here. Okay, so it goes, and then you could have oh, it's a color wheel now. Okay, that's, I don't like this. Really? Okay. So, oh, there we go. Okay. So, too many choices. So it's a monoid action. So like you could have this set, and then your monoid action could move this out. So anytime you apply the monoid action, it pushes you outside the domain. So then, you know, there's nothing to worry about when it comes to equivariance. All right, that's the silly picture. So the last thing we need for the log link, so for these log Kummer correspondences and the log link indeterminacy is the notion of free abelian groups on monoid actions. So free abelian groups, all right? Okay, so so we're going to define the following functor, free, from partially defined maps of sets to the category of abelian groups, where S, right? So where free of S, so this is also Z to the S. So this is going to be the set of elements Ni, Si. So we're going to use the notation. So I'm just trying to set up the notation here. Ni is in Z, Si is in S, I. And so this is for finitely many. Okay, so this is, maybe I could written like a direct sum symbol there. But this is what I mean by this. So note that here we will underline, so we underline S, an element of S, to denote it as an element of the free group. Okay, and so now we need to define how it behaves on maps. So given F from S to T, we get, okay, so what do we get? We get that free F of S underline. So this is, so then we extend this linearly. So this is 0 if S is not in the domain of F, and this is S underline if S is in the domain of F. So I should say this is joint work with Anton Halato. We actually played around with a couple different constructions in the, so like what you could do is you could try and define like partially defined maps of abelian groups, but this is like by far the best behaved thing that we played with in terms of functors. So if you want to do, it makes things way easier than trying to do like partially defined maps of sets, partially defined maps of abelian groups and things. You can do that, it just sucks. Okay, so we have this the free functor like so. So we can extend the functor to, so we extend it to monoid actions. So partially defined maps of sets with monoid actions. Okay, so we'll get another functor. We'll denote it by the exact same thing. To MAB. So this is the category of abelian groups with monoid actions. Okay, and so how does this work? So where we have the following, so for MS in here, so it's just a partially defined, so this is a set with a monoid action. It's an object of this category. So free MS. So this is M, of course. Then we have Z to the S, the free group on S. And the action is the usual one. So M dotted with, if I take a combination of elements, so this is defined to be the action that extends linearly. And so and then we have to define what it does to maps. So then this is just the natural map. So it's the natural. Sorry, then free FG is well, the obvious map, the natural map of monoids with abelian group actions. Okay, so we have a map of, so the partially defined map of sets induces a morphism of abelian groups, right? And the monoid actions, so the monoids are already a morphism of monoids, and so the map will be equivariant. Okay, that's, and then things will map to 0, so it doesn't really matter.